right, this lesson is about complex eigenvalues and complex eigenvectors. If you remember, we had a theorem that said complex eigenvalues always have complex eigenvectors. So it shouldn't come as a big surprise as we're working with these complex eigenvalues that we turn out to have some complex eigenvectors. If you'll also remember, we had a theorem that said that complex eigenvalues occur in conjugate pairs. We also talked about the fact that when we have complex eigenvectors, they are also complex conjugates. I'll show you what I mean with a few examples in a minute. Let me remind you of some other things that we've already learned. The definition, AU equals lambda U. That was where A was the matrix. This U right here is an eigenvector. And the lambda right here was an eigenvalue. It might have seemed trivial at the time, but this is going to be really important, and we're going to use it whenever we're given an eigenvector and a matrix. Using the definition is definitely going to be the way to go, especially with these complex numbers. And here's why. Because if I have multiples of a complex number, it's really difficult to recognize that they're multiples. It's not like good old real numbers. Something like if I have 1, 2, well, I can easily tell that 2, 4 is a multiple of that. And so is 5, 10. These are all multiples. On the other hand, if I give you something like these three vectors, can you tell that they're multiples of each other? I have 1, or I plus 1, 2i minus 3. It actually turns out that if you multiply this vector by I, you get this vector. You get negative 1 plus I, negative 2 minus 3i. They look pretty different. I mean, some signs have changed, and it looks kind of odd. And then, if I were to multiply the original by 2 plus I actually get this vector over here, 1 plus 3i, negative 8 plus I, which looks completely different. So those are actually all multiples of each other. My I, even as experienced as I am with math, doesn't recognize those as being multiples. I would have to test them. I'd have to do some arithmetic to really see that they're multiples. Unlike up here, oh yeah, 1, 2, and 2, 4, come on, you can all tell those are multiples pretty quickly. But these ones at the bottom are also multiples of each other. Now this means that when I'm multiplying matrices times vectors and trying to look at all this stuff with the complex numbers, I'm going to have to do a little bit of work to really make sure that they really multiply out like they're supposed to, or like I think they should. Okay, so now that I've reminded you about the definition and about some of our theorems, let me also remind you how to find eigenvectors and eigenvalues if we're asked to just find them cold. To find eigenvalues, we want to set the determinant of A minus lambda I, and that was where I was the identity matrix of an appropriate size equal to 0. And then to find eigenvectors, for a particular eigenvalue, we're going to want to reduce A minus lambda I on the left and then zeros on the right. Okay, now that doesn't mean that's the only approach we have as an option. Here's what I'm talking about. Say that I give you a matrix and I give you an eigenvector. And so this is the eigenvector. Obviously, this is the matrix. And I ask you to find the eigenvalue corresponding to that eigenvector. Find the eigenvalue corresponding to this eigenvector. That was the Department of Redundancy department there. Okay, well, I could go through this process. I could do the eigenvalues. I could actually go through the trouble of finding the determinant of A minus lambda I, set it equal to 0, work it all out. I know I'm going to get a complex eigenvalue, right, because I have a complex eigenvector. But I don't know which of the two we're talking about. Well, then I could actually go through the trouble of finding the eigenvectors, but I'm going to get an equation, because remember I always get infinitely many. Okay, that means that I'm then going to have to test and see if this is one of the ones that we're looking for. And if it isn't, then I know it's the other one. It's just a lot of work. Instead, let's use the definition. AU equals lambda U. The A we're talking about is 3, -2, 4, -1. The U is this eigenvector. And my question is, what would lambda have to be to make that work? Okay, well, let's work it out and see. Okay, I'm going to circle my rows so I don't mess up. 3 times 1 plus 2i would be 3 plus 6i. And then I want to add to that -2 times 3 plus I. That would be -6 minus 2i. So working out the left side. Okay, then I want to do 4 times 1 plus 2i would be 4 plus 8i. And -1 times 3 plus I would be -3 minus I. Just double checking myself here. And that is, simplifying, 3 minus 6 is -3. 6 minus 2 is 4, so I get 4i. So -3 plus 4i. And in the bottom, I have 1 plus 7i. Okay, so that was the left side. And I want to try to find a value lambda that I can multiply by that same vector and get this vector here. Okay, well, that gives me two equations that I could solve. Sometimes in some problems you'll find one equation to be easier than the other. But I'm just going to go ahead and go for the top one. I can always check it with the bottom equation just to make sure I didn't make a mistake. But here, lambda, if I divide, is going to be negative 3 plus 4i over 1 plus 2i. Okay, I can't leave it like that, right? So I'm going to have to work that out, do a little arithmetic, and that's what that last section was about. In order to divide complex numbers, I multiply by the complex conjugate of the denominator, top and bottom. So I'm going to do negative 3 plus 4i over 1 plus 2i times 1 minus 2i over 1 minus 2i. Okay, working that all out, we get on top negative 3 plus 6i plus 4i minus 8i squared. In the denominator, I get 1 minus 4i squared, which is, okay, remember the I squared is negative 1, so this actually becomes plus 8. Plus 8, and the 3 here becomes a 5. 6i and 4i is 10. So that's 10i, and that's all over 5, because again, the I squared is a negative 1. So this is 1 plus 4. And so when I work it all the way out, I finally get that lambda is 1 plus 2i. Okay, do I believe that? You know, I could have made a mistake. Let's check. Okay, so I've got this as what I think is the answer. Let's check using the second row. In the second row, I have 1 plus 7i equals this lambda that we supposedly got times 3 plus I. Now I could divide again. I could divide 3 minus I over to this side and see if I get the same lambda when I work it out, or I can just plug in what I got to check. Is 1 plus 7i equal to 1 plus 2i times 3 plus I? That's the question. Well, let's see. On the left side, I'm getting 3 plus I plus 6i. Ooh, I plus 6i is 7i. That's a good sign. And then last, I get plus 2i squared. And what is 2i squared going to be? Well, the I squared is negative 1, so that's going to be minus 2. 3 minus 2 is 1, so I get 1 plus 7i. It really does work. So this was the eigenvalue we were looking for. So now let's take a look at a problem where we're looking for eigenvalues and the corresponding eigenvectors, and we'll actually work it all the way through. So we're not given any eigenvectors or anything to go on. So our matrix is 1, 3 in the first row, negative 1, negative 2 in the second row, and I want to find my eigenvalues corresponding eigenvectors. Let's start with eigenvalues. So I want to set the determinant of 1 minus lambda I equal to 0. That's going to give me an equation, 1 minus lambda times negative 2 minus lambda, and then minus negative 3 is going to be plus 3. That equals 0. Okay, let's keep working it out. We have negative 2. Outer is minus lambda, inner is plus 2 lambda, and the last would be plus lambda squared, and then plus our 3. That gives us the characteristic polynomial of lambda squared. This gives me plus lambda, and that gives me minus or plus 1. Obviously this doesn't factor, so I'm going to have to use my quadratic formula. It's negative b, so that's negative 1, plus and minus the square root of b squared, which is 1, minus 4 times a, which is 1, times c, which is 1, all over 2a. So that's just 2 times 1. This gives me negative 1 plus and minus the square root of negative 3 all over 2. Not as pretty as I would have hoped, but maybe it'll work out. That's the same thing as negative 1 plus and minus I root 3 all over 2, or you can write it as negative 1/2 plus and minus I root 3 over 2. So those are my eigenvalues. Now I need to find corresponding eigenvectors. Let's pick one and just do it, and then remember the fact that our complex eigenvectors occur in conjugate pairs just like our eigenvalues, and we won't have to work them both out. Here's what I mean. So I'm going to choose lambda is negative 1/2 plus I root 3 over 2. And I'm going to find the corresponding eigenvectors. Okay, remember what I do is I want to reduce a minus lambda I on the left and zeros on the right. Okay, well that means that I will have 1 minus this crazy lambda value we have, negative 1/2 plus I root 3 over 2. And then the next entry was a 3, and I want to put zeros on the right. I had negative 1, negative 2 minus this crazy lambda value, zeros on the right. That looks kind of bad. Doesn't really look like something I want to reduce. But if we'll use our knowledge that we've learned in previous sections, it's not as bad as you might think. Let me just as a little aside remind you, back in the days of good old x and y, when you had x plus 2y was 5, for example, and then you saw 2x plus 4y was 10, what did you think? Those were what kind of lines? They're the same line, right? I just multiplied by 2, and so if I were to graph this line, and then I graph this line, they're right on top of each other. I have infinitely many solutions. Okay, so if you will recall, these were coinciding lines. Infinitely many solutions. How many eigenvectors do we have? So if we're working this problem up here, and I can see I only have 2 equations that we're dealing with, I'm supposed to get infinitely many answers, right? Can you apply this knowledge to this situation? These are really multiples of each other, these 2 equations. Now I do want to simplify them. Let's do that. But really, these 2 equations are the same equation. So this turns out to be 3/2 minus I root 3 over 2, 3 and 0. And the bottom row turns into negative 1, negative 3/2 minus I root 3 over 2, 0. Okay, just simplifying. Since I know they're really the same equation, if I'm really interested in reducing this, I know I'm going to get a row of zeros. Because I know that if I could multiply one row by the right number and add it to the other, it's going to cancel out. Okay, so what I'm going to do is I'm going to go ahead and skip to the section where we just go, okay, let's switch them. I wanted to switch them because this guy's a 1, and usually we like that. If I had some reason, though, to check another equation against this one, I might want to use the top row. If I needed a real number in front of x2 instead of in front of x1, I would use the top row instead. But I know that it's going to zero out, so I'm just going to go ahead and zero out that bottom row. Now, if you really want to go through the, R2 minus blah, 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 R1, you can, and you'll find out magically it all cancels out. so it's not a big surprise. Okay, I just have one more step to do to make this reduced, and that's negative row 1. That's going to give me 1 positive 3/2 plus I root 3 over 2, and then 0. It's my top row. Because all I'm really interested in is the equation. I really could have stopped earlier and used either one of these equations as my eigenvector equation. Okay, so now let's take a look at what our eigenvectors are going to look like. So remember, this is for negative 1/2 plus I root 3 over 2. This equation is x sub 1 plus 3/2 plus I root 3 over 2 times x sub 2 equal to 0. And if you remember the way that we do things in linear algebra, we always solve for the variable on the left. So I'm going to solve for x sub 1. X sub 1 is negative 3/2 minus I root 3 over 2 times x sub 2. And I have to account for every variable. A lot of people forget to do that. X sub 2 is x sub 2. So when I go to write an eigenvector, x sub 1, x sub 2 is negative 3/2 minus I root 3 over 2 times x sub 2, and then x sub 2 is x sub 2. I can factor out my x sub 2 and get that this is negative 3/2 minus I root 3 over 2, 1 as the second entry, and then that's times any value of x sub 2, except I don't want to use 0. We had a theorem that said we can't have a 0 eigenvector. Okay, so there's an example of an eigenvector corresponding to lambda is negative 1/2 plus I root 3 over 2. We could multiply that by anything we want except for 0, and we might get another form. For example, I might recommend you multiply by 2 so that you get rid of these fractions, but any multiple of this other than the 0 multiple is an eigenvector. What am I going to get if I do this for lambda is negative 1/2 minus I root 3 over 2? Do I have to write this all out and reduce again? No. I know that complex eigenvectors occur in conjugate pairs, just like the eigenvalues. And so that's going to have eigenvector negative 3/2 plus I root 3 over 2, 1. Okay, so complex conjugates here, complex conjugates there. And that's less work for me. All right, so let's take another look at this example. This was back from section 4.3, right at the end of the lecture. I gave you this matrix, and we found the eigenvalues. The eigenvalues for the matrix 1, 0, negative 1, second row 0, 2, 2, third row 0, negative 1, 0. The eigenvalues were 1 and 1 plus and minus I. If you don't remember how to find those, go back to the end of the lecture 4.3. Let's say now that I want to find the eigenvectors for the two complex eigenvalues, 1 plus and minus I. Now, just like in the last example, I'm not going to go through and find both. I'm just going to find one and then use the fact that I have complex conjugates. So let's work it out for one or the other. I'm going to choose lambda is 1 plus I. And I'm going to reduce A minus lambda I on the left, zeros on the right. Okay, so that's going to give me 1 minus 1 plus I, 0, and then negative 1 on the top row. The second row I get 0, 2 minus parentheses 1 plus I, then 2, and then 0 at the end of that. And the bottom row I get 0, negative 1, and then 0 minus 1 plus I, which would just be negative 1 minus I, and then 0 at the end. Okay, so I want to reduce that. It might look scary at first, but remember, let's use the fact that we have infinitely many solutions. So after I simplify this, let's be smart about it. Okay, 1 minus 1, 0. So on the top I just get negative I, 0, negative 1, 0. Second row, 0. 2 minus 1 is 1, minus I, and then 2, 0, 0, negative 1. Okay, negative 1 minus I we already worked out, 0. Okay, I know that to reduce it I want to start by getting a 1 in the upper left. So my first step is going to be to divide row 1 by negative I. Or you could say it's the same as multiplying row 1 by 1 over negative I. Whatever. I will get negative I divided by negative I, 1. 0 divided by pretty much anything, except for 0, is 0. Oh, what's negative 1 divided by negative I? You might think you know, and you might have some secret way of doing it, but I'm going to work it out. Negative 1 over negative I would be, remember what I'm supposed to do is multiply by the complex conjugate. That's positive I. Top and bottom. Negative 1 times I is negative I. And on the bottom, negative I times I is negative I squared. What is negative I squared? Well, I squared is negative 1. Negative negative 1 is positive 1. So I've just got negative I out of that. So just as a little aside, we figured out this should be negative I and then a 0 at the end. Second row, I'm just going to bring everything down. Okay, for my next trick, I want to get a 1 in the 2, 2 position. So I want a 1 where this 1 minus I is. Now I could divide row 2 by 1 minus I. Nothing wrong with that. We could work it all out. It just gives us a little bit of arithmetic to figure out what 2 over 1 minus I is. But a smarter move might be to just switch these two. Because if you notice, I already have negative 1 here in the 3, 2 position. And so it would be really quick to make that a positive 1 just by multiplying by negative 1. So I'm going to switch row 2 and row 3. Okay, so now you can see to get a 1 there, all I have to do is negative R2. And you could have done those in the same step. It would have been fine. We're almost there, believe it or not. Okay, I can use the fact that look at the third row versus the second row. I know that those are really multiples of each other because I know I have to get infinitely many solutions. And in order for that to happen, I know that bottom row is going to 0 out. Now, if you want to go to the trouble of really proving it, you can. You would do row 3 minus 1 minus I times row 2. And if you actually work that out, you will really see it's not just coincidence. It really does 0 out. If you wanted to skip that step and go ahead, once you get the zeros here in the first column, if you wanted to go ahead and 0 out the third row, it would be fine. Okay, so now I've got it in row reduced echelon form. Let's write out our equations. First equation, x sub 1 minus I times x sub 3 is 0. Second row, x sub 2 plus 1 plus I, x sub 3 is 0. Remember we always solve for the one on the left? Let's do that. This means x sub 1 is I x sub 3. X sub 2 is negative 1 minus I x sub 3. And don't leave out x sub 3. X sub 3 is x sub 3. Now let's write it into a vector. X sub 1, x sub 2, x sub 3 is I x sub 3, negative 1 minus I quantity times x sub 3, and x sub 3 is x sub 3. Let's factor out our x sub 3, and we'll get the vector I, negative 1 minus I, and 1, all times x sub 3, where x sub 3 can be any value except for 0. Okay, so there's an eigenvector, or any multiple of that other than the 0 multiple, that is corresponding to the particular eigenvalue we chose. Let's write that down. We chose lambda was 1 plus I. Its corresponding eigenvector is I, negative 1 minus I, and 1. Or any multiple of that other than the 0 multiple. Now, what would I get for lambda is 1 minus I? The corresponding eigenvector would be the complex conjugate. Now, for I, remember it becomes negative I. Negative 1 minus I would become negative 1 plus I, and then 1 is still 1. All right, so there's an example of complex eigenvalues again, and then complex conjugates for eigenvectors. All right, so I tried to remind you how to find eigenvalues if you're given a matrix, how to find eigenvectors if you have your eigenvalues, and also how to find an eigenvalue if you're given the matrix and an eigenvector. Don't forget your definition, AU equals lambda U. That can really get you out of a bind, especially if you have a bunch of choices to try. Rather than having to try them into these crazy equations and see if they fulfill all your conditions here, just go up here and check. You know, if I multiply out the left side here, does it equal the right side? And often this will be much faster for you.